Now let's do an analysis of delta H, delta S, and delta G for the dissolving of ammonium chloride solid and analyze or talk about the results. And so first off, I've got a dissolving reaction, something we've talked about before, and it shows the solid going to the two ions. And from there, I went to our new table for thermodynamic and electrochemical values that shows delta H, the change in enthalpy of formation, the entropy standard, and the change in free energy of formation. And I looked up all the values, and I got these. Now, all the coefficients are 1 here, so to calculate delta H reaction, it will be products minus reactants, and I get 133.3 minus 167.1, good, plus 314.4, I get 14.0 kilojoules per mole. This is an endothermic reaction. And an endothermic reaction tends to not to be spontaneous. And other things we can say about this, and if this were on the exam, it wouldn't just say analyze the results. It would have a specific question on it. But we know this is an endothermic reaction. We also know that if this reaction occurred, the reaction would take in energy from its surroundings, and we would feel this reaction to be cold. So that's another thing that we can say about it. Now let's do delta S reaction, delta S not reaction, I guess. The change in entropy of reaction at standard conditions. And now it's going to be products minus reactants. 111.2 plus 56.6 minus 94.6, 73.2. And those are joules per mole Kelvin. And so entropy increases. Which we may or may not be surprised by. I don't think we should be too surprised by because we're taking a solid and we're turning it into aqueous phases, which are distributed apart in the solution. So that generally makes sense. When entropy increases, it tends to be spontaneous. Tends to be spontaneous. And now delta G naught reaction, products minus reactants, 79.3 minus 131.2 plus 202.9 minus 7.6. Kilojoules per mole. This is a negative number, and we're at standard conditions, so at 298 Kelvin, which is 25 degrees Celsius, this reaction is spontaneous. Good. I have put ammonium chloride solid in solution before and watched it dissolve, and so our experience must also relate to what we're calculating here, and whether or not you've done it before. You have done it. Have you done it? No. But you've done it for sodium chloride, and so we could answer that question for sure for sodium chloride because we have watched it, so it better tell us that dissolving is spontaneous. Also true for me for ammonium chloride. All right, now what else can we say? We can say that because one of the thermodynamic functions, the change in enthalpy of reaction at standard conditions, tends not to be spontaneous, and the other one, the change in entropy of reaction under standard conditions, tends to be spontaneous. Then when these are different, meaning one tends to not and one tends to be, then there will be a temperature at which the reaction changes from spontaneous to non-spontaneous. And I think that's what we're going to do now. So I'll keep these handy, and let's now talk about estimating delta G naught reaction at temperatures other than 25 degrees Celsius. And so we could ask the question at 100 degrees Celsius, is this reaction spontaneous? And what is delta G naught reaction? And I'm going to leave the naught in here. I know we are not at standard temperature anymore, but we will be even less standard later. So I am aware that we're not at standard temperature, but we're going to keep it around for now. That's, again, how I do it for consistency's sake. But let's go ahead and do that. So we have delta H, we have delta S, and we're going to plug it in and do delta G equals delta H minus T delta S. And now we'll plug in numbers. So, and as I've talked about before, I'm a joule man. I work everything in joules or kilojoules. I suggest you pick one if you haven't already. So 14.0, there's a dot in there. 14.0 kilojoules per mole is 14,000 joules per mole. Our temperature is 100 degrees Celsius, which is 373 Kelvin. And our delta S is 73.2 joules per mole Kelvin. And now plugging this in and solving. $14,000 minus 373 times 73.2 is minus 13,300 and 3.6. That's joules per mole. As much as I love joules, I tend to put them back into kilojoules. And I get minus 13.3 kilojoules per mole. We can say two things. One is, yes, it's spontaneous. And two, we could even say it's more spontaneous or free. You could get more free energy out of this reaction if it's done at 100 degrees Celsius. Now, let's ask something else. Let's ask, at what temperature does this reaction change from spontaneous to non-spontaneous? And I'm going to abbreviate spontaneous as spon. So at what T does this reaction change from spontaneous, spon, to non-spon? And it changes from spontaneous to non-spontaneous when delta G equals 0. Another way of looking at this is that it changes, that this reaction goes through an equilibrium point because delta G equals 0 at this temperature as well. So we could also say, at what temperature is this reaction at equilibrium? That's not typically how we ask this, but we could, because that's what 0 for delta G means. And what we do is we set this equal to 0. We plug in our values. So 0 equals delta H, minus T delta S. And then we will now plug in our values, 14,000. We will plug in T, because we're solving for T. We'll put our 0 for delta G. And now we'll solve for temperature. You can see that when we put this over to the other side, this term will be positive. Temperature ends up being delta H divided by delta S. 14,000 divided by 73.2, I get 191 Kelvin. And a couple things we'll say about that. This is the temperature at which it changes. However, this is just an estimate because we're talking about aqueous species. And at 191 Kelvin, water has turned into ice a lot of temperatures, a lot of degrees Celsius, and a lot of Kelvin before that. So this is an estimate that does not take into account physical reality. We always want to check with physical reality to see if this is actually a possibility. But that's the suggestion anyway, and that's our estimate. Okay, let's do the same thing for photosynthesis now. Take a minute and make sure you've got all these in your notes. Pause the video if you will, and then let's go ahead and calculate for this one, which has some 6's. So delta H, delta H naught reaction is going to be products minus reactants times coefficients. So it's going to be minus, well, I better write this one out. Sorry, this number is not the number that's on your sheet. Let me update it before I solve this problem. Oh, no, it is the number that's on the sheet. Good. So times 1 plus 6 times 0, so we don't have to include this, minus 6 times minus 393.5 plus 6 times minus 285.8. Multiply all these out, 1273.3 negative. These are all going to be pluses due to the double negatives. So plus 6 times 393.5 plus 6 times 285.8, 2802.5. kilojoules per mole. Very endothermic. Not a spontaneous reaction according to delta H. Delta S, and let's see, so products minus reactants, so it's going to be this plus 6 times the 205, 212.2, plus 6 times the 205.2, minus 6 times this, 213.8. Sorry, let me get, there we go. Minus 6 times the 69 equals minus 258.8. And what we can see is this, so entropy decreases. Both of these tend to be non-spontaneous. Therefore, delta G, so, well, let's calculate delta G. But I bet it's going to be positive. 910.4 minus plus 6 times 394.4 plus 6 times 237.1 minus 2878 or sorry, positive 2878.6 kilojoules per mole. This is non-spontaneous. At 298 Kelvin, that's standard conditions. And then, because both of these tend to be non-spontaneous, this reaction is non-spontaneous at all temperatures. Because delta H and delta S both tend to be non-spontaneous, this reaction is non-spontaneous at all temperatures. Non-spon at all temperatures. And another way of looking at it is, so if we look at our equation, delta G equals delta H minus T delta S. Delta H is positive. Delta S is negative. Temperature is always positive, so this term will always be positive as well. Delta G will always be positive. One more example. You can see we're hitting this pretty hard. You can count on seeing this again. Vaporization of water. Is it spontaneous? At 25 degrees Celsius, at any temperature. And we do have some familiarity with this. Let's calculate our, and I'll just put my delta H, my delta S, and my delta G at the end here. It's all going to be product minus reactant. So minus 241.8 plus 285.8, 44.0. Endothermic. We expect that when you take a liquid and turn it into a gas, you're separating the molecules. You're going to have to put energy in to do that separation. I'm going to squeeze this in. This is endothermic, which tends to be non-spontaneous. Under standard conditions, of course. Well, delta H tends to be non-spontaneous at all conditions. It's a constant. It doesn't change as a function of temperature. This one here, gases, of course, much more dispersed matter-wise than liquids, so higher entropy. 118.9 joules per mole Kelvin. Favors being spontaneous. And delta G, 228.6 minus plus 237.1, 8.5. Okay, so what does this say? So let's see. It says So at 298 Kelvin and standard conditions, this reaction is non-spontaneous. Okay? And what that means is that at T equals 25 degrees Celsius, P, partial pressure over H2O, equals 1 atmosphere. This reaction is non-spontaneous. Okay, and you may have questions about this, but let's keep going. So, 2, because it's endothermic, which tends to be non-spontaneous, and also the entropy increases, which tends to be spontaneous, there is a temperature above which this reaction is spontaneous. And we'll solve for it in a minute. Let's see, and in fact, let's do that now. So to find the temperature at which the reaction is spontaneous, you set delta G equal to 0. You plug in your values for delta H and delta S, and then you solve for temperature. We have 44,000 joules per mole minus T, 118.9 joules per mole Kelvin equals 0. Bring this term to the other side, solve for T. You're going to get 44,000 divided by 118.9. 370 Kelvin, which is 97 degrees Celsius, 373 being 100. Again, this is an estimate, remember. But what this is saying is that at 97 degrees Celsius, this reaction, and above, T greater than 97 degrees Celsius, this reaction is estimated to be spontaneous. There we go. Spontaneous. Not bad using only thermodynamic quantities, because at the boiling point, which is 100 degrees Celsius, is when this reaction truly becomes spontaneous. So not too bad, not too shabby. And then one other term I wanted to talk about is the fact that this reaction is driven by entropy. This reaction is entropy driven. And I'll put entropy driven in quotes. It's a term that we need to know. So entropy is tending to be spontaneous. So it is driven to be spontaneous, or this is entropy driven to be spontaneous at higher temperatures. And in general, the term in this equation that, here we'll take out the 0, the term in this equation on the right-hand side that tends to make it spontaneous is what's called driven. So the reaction can be entropy driven if delta S is positive. It can be enthalpy driven if delta H is negative. It can be driven to be spontaneous by both of these terms or neither of these terms. Now, here's a finer detail. So let's come back to number 1. It says this reaction is non-spontaneous at 25 degrees Celsius and partial pressure of H2O equals 1 atmosphere. What we will find is that under typical room conditions, the partial pressure of H2O is less than 1 atmosphere, significantly less, meaning we're not at standard conditions, and this reaction will be spontaneous because water will evaporate. So there's something we're still missing here, right? We've figured out when a reaction is spontaneous in terms of standard conditions, but what if conditions are not standard? Because conditions are usually not standard, but we're getting there. See, is there more to do? Next time.